A pleasant day. Presenting for Online Jamb Class Academy, OJCA, I am your chemistry teacher, Christopher Gonzel. And today we'll be looking at Hess's law and enthalpy changes. At the end of today's presentation, a student should be able to 1. State Hess's law, and 2. Calculate the enthalpy changes in reactions using Hess's law. Now, what exactly is Hess's law? What does it state? Hess's law states that the total enthalpy change, that is, the total energy change in a reaction, is fixed. In other words, the total energy change in a reaction does not change. Its value remains the same, irrespective of the route taken for that reaction. In other words, if we have a reaction wherein A reacts with B to form C, and that reaction requires a certain amount of energy, let's call it E1, but then we can produce C alternatively from A and B instead of going the direct route wherein we combine A and B and that gives C. If C can be produced alternatively from A and B, wherein A and B can react instead to form D and E, and then D and E be converted to C, what Hess is saying and proposing is that the energy involved in converting A and B directly to C is actually equivalent to the sum of the energies involved in producing C indirectly. In other words, E1 here, this energy is actually equal to E2 plus E3. And if that being the case, what we can therefore say is that the reaction A plus B to give D and E, that is this reaction here, plus D and E to give C, this reaction here, must therefore then be equal to A plus B to give C, that is this reaction here. In other words, this reaction, the direct reaction, is equal to the sum of the indirect reactions, this reaction and this reaction. And let's look at it. A plus B to give D and E, if we add that reaction to D and E to give C, the other reaction, then what we have here on the left hand side would be A plus B plus D plus E. That's all we'll have on the right hand side if we add everything that obtains here on the left hand side. My apologies, on the left hand side we'd have A plus B and D plus E. And over on the right hand side what we'll have is D plus E plus C. And so this is what we'd obtain. In chemistry, we have been taught, and we should know, that if a species appears on both the left hand side as well as the right hand side of an equation, it does not participate in the reaction and is therefore referred to as a spectator ion, or spectator species in this case, and can be eliminated. And so when we look at what we have here, D finds itself on the left hand side but is also on the right hand side, so we can therefore eliminate D. The same thing obtains for E. E appears on the left hand side but also finds itself on the right hand side, and so E can be eliminated. So therefore we can eliminate both species D and species E, and what that will therefore result in, so on our left hand side what we'll have remaining after D and E have been eliminated would just be A and B. And over on the right hand side, after D and E have been eliminated, what remains is just C. And so what we have here is A plus B giving C. In other words, the sum of these two equations, which are the the equations involving the indirect root, are actually equal to the equation of the direct root. And therefore, the enthalpy values of those equations is actually equivalent to the enthalpy value of the direct reaction. Now, what is the application of Hess law? What is the utility? Hess law can actually be used to calculate the enthalpy change of a reaction that cannot be determined directly experimentally. In other words, if this reaction here, A plus B to give C, cannot be determined through experiment, but instead we know the enthalpy value of A plus B to give D and E through experiment, and also D plus E to give C through experiment, we can therefore determine the enthalpy value of this reaction by indeed adding the enthalpy value of this reaction with the enthalpy value of that reaction right here. And this would be equivalent to A plus B to give C. Let us look at an example.